Science truly is everywhere, and there's no better example than granular physics. It's the summertime right now, and people are going out for vacations at beaches. And one of my personal favorite things to do at the beach is to build sandcastles. But how do you build the perfect sandcastle? What's the perfect amount of sand and water? And how does this concept apply to things in our everyday life, like the ground that we sit on and even the mixed nuts in your pantry? Well, it all has to do with granular physics, or how these different substances move and how these interesting substances take different shapes and forms. And to learn more about granular physics and to learn more about sand and other of the more of these substances, I'll be talking to Mr. David Meer. He is a graduate student in physics at Emory University, and he studies how all these granular fluids and soft matter move. And we'll get more answers to some mind-blowing questions in this episode. Let's get right into this interview. Let's go. Hi, Mr. Meer.
Hello.
How are you doing today?
I'm really good. Thank you for having me here.
Yeah, thank you so
I
much for
really,
joining me.
I really enjoyed meeting you. I guess it was Saturday. Yeah.
Yep, I really enjoyed meeting you in person. And now I'm talking to you through my podcast, Spectacular Science. I really want to interview you because of your amazing research and one other thing. It's summertime here in the US, and most
hmm
people are probably heading over to the beaches to have some fun. And one of the things you talked about was sand and granular physics and the perfect amount of water in the sand to make the perfect sandcastle. So we're going to get to that later in the episode, but first, can you please introduce yourself to the listeners?
Hello, everyone. I'm David Meer. I'm a graduate student at Emory University. I'm in my third year out of probably five or six. I graduated from State University of New York at New Paltz with majors in physics and astronomy and minors in history and geography. And yeah, I'm a third year in the physics program, and I'm working under Dr. Eric Weeks and I'm working in his soft matter laboratory where I focus on granular physics, but more generally soft matter as well.
That's really cool. So, how did you get interested in science?
I think for me, it started from a very early age. So my mother did undergrad in physics. She eventually had to switch, but it started in it started in physics and then moved on. But like when I was a kid, she was always geeking out about like fluid dynamic simulations, and like she had like a little iPad app that was just like a bunch of particles moving around, and you could just swipe them or push them with your finger and see them react and all sorts of stuff like that. My mom got me into like fluid mechanics and stuff like that very early on. So really that connects perfectly into soft matter, because soft matter is like fluid dynamics is a huge component of that field.
Yeah, and that's really interesting. We'll get more into that later in the episode and get deeper into the science of granular physics. But what do you study in your lab specifically, and what specific research do you do?
Yeah, so the lab in general studies like soft matter physics. So when people think of physics, they often think about like, little quantum particles, like they're smashing atoms together, dealing with like electromagnetism and, these very complicated, very intense things that you don't often experience in everyday life. Or
Hmm.
maybe instead they think of like astrophysics and like, the Big Bang and the universe and black holes. And like these things are really cool, but you don't experience them. And soft matter is neither of those things. It's neither really big, it's not really small. It is like just right at the human scale. So soft matter, like formally, is the study of non-rigid bodies, basically. So you think of a rigid body, you think of like the first physics class you take, you're pushing a block up a hill, and you don't have to worry about the block breaking in half, or you like drilling a hole in the block, or it like squishes, or anything like that. But in reality, those things happen if you try to push, if you try to push jello around on a plate, It's not going to move like a rigid block. It's not going to move like pushing a piece of metal around.
Hmm.
It's going to have some give. It's going to squish. It is going to have some elasticity. It is going to have maybe some viscosity, or maybe we want to talk about the difference between water and honey. Okay, that's relatively straightforward in that the only difference is viscosity. One's a lot thicker, it flows a lot slower. But then, like, what about mayonnaise?
Oh
Is
yeah.
yeah, is mayonnaise a just a viscous liquid? I don't think so, because if you take a spoonful of mayonnaise, it's never gonna eventually like drip out of the spoon and
Yeah.
form like a solid top. It'll like
Hmm.
keep a peak basically. And
Yeah.
keeping that peak means it's kind of rigid. It's kind of acting like a solid. We call that a viscoelastic fluid because it has some properties that are viscous like a liquid and some properties that are elastic like a rubber band. Like, you or me, we have skin that, will snap back when we
Hmm.
pull on it.
Yeah.
So we vaguely study these like complex materials.
This lab sounds really delicious. Jello, honey, mayo. What else do you have?
We have shaving cream, which
Uh,
maybe isn't so delicious.
yeah, it's not that
We have
delicious.
Orbeez.
Ooh.
We actually have a pile of Orbeez in lab. I didn't bring them to that demo day, but we've
Hmm.
got them. And we've got many, many buckets of sand, which I also wouldn't want to eat.
Yeah.
So, what I specifically research is granular physics. So, in the same way that a spoonful of mayonnaise is neither a solid or a liquid, sand might feel like it's very solid, but you can pour sand into a bucket. One of the definitions of a liquid is that it takes the shape of its container. A bucket of sand, the sand has taken the shape of its container. Any individual piece of sand is very clearly a solid, but as a bulk, they act different. And that, kind of makes sense. For the mayonnaise example, there are little tiny pieces of, solid fat or liquid water, but then combined, they act different. Sand is the same way. So I study granular physics and what are the properties of granular materials? How densely can you pack them in? How does fluid like move through these different things? Like if you want to study how far is water going to invade into soil or into the beach, you need to know, well, how dense is that sand? What shape is the sand? What material is the sand? What's the difference between the biggest rock and the smallest tiny, bit of soil? Questions like that.
Yeah, and the best part about this science is that it's used in our everyday lives. You don't have to go
Mhm.
looking for a black hole in your backyard.
Yeah,
You can just pick up some sand from the beach or anywhere, and you can experience granular physics. And you don't need any explosives or atom colliders in your lab. You
yeah,
just need sand, which is really really
yeah.
cool. And that leads us into our next question, which is why is it important to study granular physics?
Yeah, so I want to like bounce off of that and like give other examples because it's not just sand. It's not just like relevant for oceanographers and beachgoers. Like it is the soil. If you're working in agriculture, you need to know how well if you're farming, if you're like a construction worker, concrete is fairly complicated, but it acts
Hmm.
a lot like a granular material as well. There's a lot of things in concrete, but granular materials, sand is one of the major components of concrete. You have, if you want to make glass that is melting sand, just straight up. The soil, like the bedrock that we put buildings on, is sand when there, or is soil. When there's earthquakes, you almost like liquefy the soil and it acts kind of like a fluidized bed of sand, which you know what it is. But
Hmm.
to the audience, if you look up a fluidized bed of sand, if you pump air through sand, you can get it to almost look like it's boiling and sloshing around like it's well and truly a liquid, but no, it's just sand with a bunch of air through it, and that sort of violent process can get triggered during an earthquake.
Yeah,
Um,
and all of these things they happen right under our feet, and
mhm,
you don't have to go anywhere to find granular materials. They're either
yeah,
in your stomach after you eat them, of course, or under the ground, and you trust granular materials as you walk. So that's a really
yes.
big thing.
Now, I there's that's like the application side of stuff, but also on the physics side of stuff. You often hear about, fundamental physics, and that goes back to the atoms and the particle colliders. Um, and there's a whole kind of thought process of, the universe is deterministic. If I knew where every atom was and how every atom would react, I can predict everything. And on some level, that's true. But as we see in, larger experiments, once you get past a couple of atoms, things get too difficult. When you get to hundreds or thousands of atoms, things get chaotic. Things start to behave in ways that are really, really hard to predict just by looking at, well, this atom is attracted to this atom and repelled from this.
Yeah,
So there's a whole field of talking statistically. Okay, I don't know what any individual grain of sand is doing, but statistically, they're falling out of the bucket. I don't know what any little bit of air is going to be doing, but statistically, I can feel temperature. I can feel it pressing on my body. So I don't need to know exactly where every single air molecule is in the room to know that it's, 70, 80 degrees outside. So granular materials and soft matter is part of kind of a bigger kind of field of study of emergent phenomena. So even though you have the individual rules of how atoms behave, that can only tell you a grain of sand is going to stick together. It's not going to, fall apart.
mhm,
That doesn't tell you that a bucket of sand can act like a liquid. You need to look at an entire group of particles and think about all the different behaviors that are in that group. And basically from there, when you look at the bulk, you can start to see new things that no one would have ever predicted. And that can
yeah,
be
it's
things
really
like
interesting.
forming glass, that can be things like these non-linear or these non-Newtonian fluids, so many things. And it's not fundamental physics, but it's still predicting things that otherwise we wouldn't have any way of understanding.
Yep, and that's the really cool part about this field of study. So now getting into the juicy science. Why do granular things such as sand act in weird and interesting ways?
So yeah, that's kind of getting into part of it. Is the kind of when you look at a bulk, it's all, it's hard to predict, but also granular things are gross and nasty and slimy and jagged and all different sizes. And there's a lot of difficulty in understanding all of that because, let's the simplest system you could do, the simplest system that physicists like thinking of is okay, what if every single bit of sand was a nice little sphere and they're all the same size and they're like little marbles? What's the behavior of the marbles? Okay, you can do physics on that. You can work on that and do all sorts of things there. There is probably 50 PhDs out there that are just studying monodisperse, everything's the same size, glass beads, basically. But then what happens if a single one is large? What if you put in a single rock into your pile of sand? That creates a whole new problem because now this one grain is acting differently. What happens if you put one in that's a lot smaller? Then you can have some sort of lubrication effect where it's easier for two big marbles to slide past each other if there's little guys in between. So what I specifically focus on, and I actually published a paper about this last Monday, so I'm really happy about this. Um, I published a paper on the effect of adding in different sizes and what those different sizes do, how much space they take up, how much water you can move through soil if you have lots of little tiny things as well as a couple of huge particles. Um, but still, that research was only on circles. You can do the exact same thing with rectangles or triangles or hexagons or like weird, like crescent moon shaped things or plus signs or, I could keep it with ovals. Like you could work on any of these different systems, and each one has like a whole world of complexity within it. So we are a long ways away from being able to like accurately model like in perfect theory the behavior of just a pile of sand because it is jagged. They're all different shapes, they're all different sizes. Maybe some of them are stuck together, some of them aren't. Maybe there's a little bit of water in the sand that's holding them together. Like there's so much complication there, and my one little section is when you have perfect little circles and they're all different sizes, how does that change the density of them? So there's just like so many different parameters. Are we pushing the sand or are we just looking at it standing still? Like these end up being very different things with very different results. Yeah, so there's a lot of complication there. And every single thing I just named is probably at least either three people's PhDs or there's gonna be three people in the future who are gonna study those things.
Yeah, and there's so much variability that's hard to track because you have to
Absolutely.
have if you just take, let's say, a container of sand, there's big pieces, there's small pieces, there's jagged shaped pieces, there's so many different things that could impact how the entire thing as a whole, as you said, the generalized picture of it, it's
Yeah.
gonna look different.
And how do you run experiments on these things? I
Yeah.
mean, like these are rocks. You can't just put a microscope in and okay, you see the top layer of rock and then that's it. You can't see any further down. So you need to come up with like bulk properties. Like let's shake the whole thing and see how it responds when we shake it, or let's run a computer simulation where we can track everything perfectly, but then we still need to find some way to compare it to real life to make sure that we're onto something because computers are great, but they only do what we tell them to do.
Yep.
So if we don't know there's something missing, we won't catch it until we check it with experiment.
Yeah, it's the real life part and also the computer part, which is
Mm,
big thing. It's kind of like how you make a video game. You have to have the sketches down, and you also have to have the prototype on the computer down, which is really, really interesting. It's so cool that people study this, like you, in labs.
yeah. No, I have a lot of fun with it. If hopefully you can tell.
Yeah, we can tell. Yeah, it's a really, really interesting field. So now we're going on to what everyone's waiting for, the recipe for a perfect sandcastle. So you're gonna reveal ages of science right now in this episode, right?
So, if you just pick up a bunch of sand in your hand and you figure out how many, like, I don't know, cups or teaspoons of it you have, however much volume you have. We did a demonstration recently where everyone picked up 100 milliliters of sand. It can hold about 35% of that total volume in water if you just keep adding water in. If you have 100 milliliters of sand, you can fit about 35 milliliters in there before it'll start like dripping out the bottom or overflowing and stuff like that. When you get above 35, that's when you basically start making mud. Because everything is fully saturated, fully submerged. Now you have bits of sand floating in water. So 35% is way too much. On the other hand, everyone knows that when you go down to a beach, you can't build a sandcastle with the stuff right at the edge of the beach. You have to go towards the wet sand. You need a little bit of hydration. So adding that hydration in, basically, there's a tiny droplet of water between two bits of sand. There's water forming a little liquid bridge, a little capillary bridge. if you guys know about like what a meniscus is in a beaker, it's the same idea as that. Water likes to coat surfaces, so it likes to coat sand. So if there's two bits of sand near each other, the water will want to bring them together and will hold them together, adding a little bit of stability. If there's too much water, if you get all the way up to 35%, um, it'll you've basically just flooded the inside and not there's not as much cohesion. So the best number that one paper calculated that I read, if everything was perfect monodispersed spheres, those little like perfect marbles I was talking about, then the best hydration is 1/8. So that's about 12.5%. Now, as I just mentioned, granular materials are very different and there's a ton of variety. So we ran the experiment on Saturday, and the consensus seemed to be something more in the range of like 20 to 25% hydration was like optimal.
Mhm.
But that wouldn't surprise me because there's so many differences between a regular pile of sand and these kind of perfect marble simulations. But if you have the perfect marbles, they've studied it and it's about 12.5%.
Yeah, and that's something you can all try at home too, or if you go to the beach or something like that, you can try all of this at home or even at a beach, and you can see what the perfect amount of water for the perfect sandcastle is. And science can only answer a little bit. It's all up to you to do all the digging and do the experiments and find out what works for you. So that's the best part about science. It's the scientific method. Just keeps going around and around and around and around, and it's really really cool. So
Absolutely.
yeah, so now moving on to the next generation of granular physicists or just scientists in general. What advice do you have for kids who are interested in science?
I think there's a lot there's so many resources out there, whether it's videos that first got me into physics, like it was Neil deGrasse Tyson's like Nova series of, astronomy things. Um, in Atlanta where I'm based, there's the Science ATL program, and there's tons of like science museums and science activities, and like there's an Atlanta Science Festival, and you can really figure out exactly what you like at places like that. Do you want to learn about the biology and how cells work, or are you a computer science person and you want to figure out how a computer thinks, or do you want to do granular physics, or do you want to understand how the human body locomotes? Like, what's going on that lets me wave my arm like this? And why can't why can't I wave my arm like this? Why does my elbow stop me from doing that? There's lots of resources out there in museums, in those videos. I really was a YouTube kid myself. I love channels like Veritasium and Smarter Every Day and channels like that, that are really great. There's a lot of science education out there, yeah, there's a lot of great resources out there. And generally, if you tell your parents, hey, I want to do science, do you think you can see if there's anything nearby we can go to? That's absolutely a good idea. And, the world of education out there has become so accessible. Like, I'm sure if you're like a high school age student, there are colleges who would love to show you their facilities and hope that you apply there one day. If you're a junior or sophomore in high school, say, hey, local college, I'm interested in physics. Can I take a look at your physics program or whatever it is? They would jump on that opportunity, because everyone wants to get the word out.
Yeah, and that's the really important thing about science communication. And all the demos that you and your lab are doing, they're a really great way to get kids and teens into science and get their hands dirty into the science of granular physics. Yeah, I had to wash my hands after that that science demonstration. There's a
Oh,
lot of
yes, I
sand.
had to a lot as well. There
Yep.
was a long cleanup. Yeah,
Yeah.
dirty labs are kind of par for the course for us.
Yeah, they're kind of normal right now, especially since you're dealing with sand.
Oh, yes.
Yep. Again, thank you so much for joining me today. I really enjoyed it, and I learned so much about granular physics and the perfect amount of water for a sandcastle. I know that's what everyone clicked on this episode for, and I know you answered the question very,
Yes,
very
that's a
well.
good title.
Yep, it's a really, really good one, and it's just amazing to see the science that we're standing on right now, and it's all around us from Mayo to the sand at the beach to the ground that we're standing on. It's just amazing. Thank you so much again.
Yeah, thanks for having me, and thanks for being part of that science education world. I'm sure
Thank
there are
you.
other people who will really appreciate this as well, and that's what we're here for.
Thank you so much. Thank you so much for listening to this episode of Spectacular Science. Spectacular Science is produced and hosted by me, Akshay Raman. Our theme song and additional music in this episode are by Chan Ramachandran. Also, special thanks to Mr. David Meer for accepting my interview invite. Thank you so much for joining me, and I had so much fun learning about granular physics and the recipe for a perfect sandcastle. Also, thanks to Mr. Meer for the amazing pictures you saw in this episode. Please visit my podcast website, spectacularsci.com, to find interactive activities, articles, and blog posts. That's spectacularsci.com. Do you have a science question you want to answer on a Spectacular Science episode and get a special shout out? Grab an adult and head over to spectacularsci.com/contact. There you can find a contact form where you can send me your amazing science questions. Thank you so much. Also, don't forget to subscribe to this podcast wherever you're listening right now. It really encourages me, and you'll be up to date on all the new episodes. Subscribe and share this podcast with your friends and family. Thank you so much. Thanks for listening, and we'll see you on the next episode of Spectacular Science next week. Keep thinking about science.